Thank you very much. Intention of this presentation is to convince you that extending scalar sector of the standard model provides a viable and perhaps even attractive possibility that solves the most fundamental difficulties the standard model is possessing, and it's an interesting theoretical alternative as well. So the outline is the following. So first, we will go through those difficulties that subjectively I consider important. Then I will spend a slide on interpretation of LHC Higgs data. So the fact that the Higgs boson discovered is standard model-like. Then I will formulate a goal of that construction. Then we will review various possible extensions of the standard model, and I will be staying within renormalizable theories. So theories that could be UV completions or just extensions of the standard model. And I will talk about singlet models, so standard model extended by addition of scalar singlet fields, either real or complex. Then I will review N-Higgs-doublet models, so extension by addition doublets. And then, I'm afraid it's dying. And then we will together construct models that indeed solves those fundamental problems. And at the end, I will summarize. I will provide summary and conclusions. Okay. Before I start, I will be citing papers or projects that I've been involved in. So before I start, I want to mention colleagues who contributed to these fields. Mostly, I think, Howie Haber would be one of them, Jack Gagnon, Gustavo Branco, Luis Lavuora, people from Lisbon, Joao Silva, Pedro Ferreira, Apostolos Pilavsis from Manchester. Over years, they contributed a lot, and many of those things somehow is rooted in what they did. Good. So, difficulties. The fundamental difficulty is lack of dark matter candidate. The standard model doesn't provide candidate for dark matter. On the other hand, experimental evidence is very strong. Experimental evidence comes from galaxy rotational curves, of course, classical evidence, from gravitational lensing, from CMB. Also, dark matter is needed for structure formation. And these are different regions of scales, different physics is involved. So I think it's fair to conclude that indeed dark matter is there, even though there are attempts known as, for instance, MOND, modified Newtonian dynamics, and there exists even its relativistic generalization as a generalization of general relativity that is trying to explain data without introducing dark matter, but this is, it exists over years and it's not successful. It doesn't explain all those data. So So I think we just conclude that dark matter is there, and let's assume that based on facts, and we will try to find the candidate. Now, another fundamental experimental fact is the baryon asymmetry. In the universe, we don't see antimatter. There is only matter observed. And that must be explained. Of course, it's possible that it's just a property of the universe. It was always asymmetric, and it's still asymmetric. So this is not what we would like. We would like to dynamically to explain observed asymmetry starting with symmetric states. And standard model cannot do that. Standard model cannot do that. There are famous Zakharov conditions that must be satisfied in order to explain that. Some of them are satisfied by the standard model itself, but the important drawback of the standard model is that even though there is CP violation through CKM metrics, of course, in the standard model, but the strength of CP violation is too weak. It's not sufficient to generate baryon asymmetry. And this is, again, an experimental fact. It's not based on some prejudice, on some hierarchy problem or anything like that. Just facts. There are other facts as well, not that strong, but the existing problems. I would mention them among existing problems. The so-called strong CP problem, right? We know that a term of that form, theta is a parameter, dimensionless parameter, times f mu nu dual. It's a legal term in that sense that it is that it agrees with symmetry, so could be added. However, this is odd under parity, and therefore it contributes to electric dipole moments. And if you calculate neutron electric dipole moment using this operator, then the result would be of that form. Since there is a limit on this, at the end we find that theta must be less than 10 to the minus 10, very small number, without any clear reason. This number could be of order of 1, of order of coupling constant, perhaps 0.1, maybe 10 to the minus 2, but 10 to the minus 10 requires understanding. So it's not as important as dark matter and baryon asymmetry, but it's also a difficulty. Dark energy, I think I prefer to be here. Dark energy is also a problem. You see, on this plot, we see energy densities on the vertical of cosmological constant versus matter. And those omegas are defined as ratios of energy densities over critical energy densities. And those colorful regions are data. And those data, as you can see, they cross somewhere here. So we can say that this is a region that would fit the data, and omega lambda, so energy density that corresponds to cosmological constant is about 0.7, dark matter and the baryon is 0.3. And now if you take this 0.7 and recalculate that in terms of energy density in GeV units, GeV to the fourth, you will find the rho lambda that is needed here in this location is 10 to the minus 46 GeV. Now, if if we believe that the explanation for omega lambda has something to do with gravity, then there is only one scale. It's a Planck mass. So you expect that rho lambda should be of the order of Planck mass to the fourth, which is 10 to 76. There is 120 orders magnitude discrepancy. This is a difficult problem. There are many parameters in the standard model. Even without right-handed neutrinos, you count parameters, you find 21. It's many, right, as for fundamental theory. And at the very end, there is an issue of the Higgs boson. Why there is one Higgs boson? The Higgs boson has been introduced pragmatically just as a minimal solution that is needed to construct a renormalizable theory with gauge theory with massive gauge bosons. But no one tells us that it's just one. It's right. We have many fermions, we have many bosons. Why single? So that's already suggests that I'm heading towards extending Higgs sector, scalar sector. And now the goal, maybe I should, what should be the goal? The goal should be to solve those first fundamental problems that I mentioned. So let's try to focus on scalar sector, and let's try to solve both the dark matter issue and the baryon asymmetry. So, in other words, extra stuff, extra particle that is stable, dark matter must be stable. So we need a stable scalar particle, since we are heading towards spin zero. So stable scalar particle, and we need another source of CP violation, because the CP violation from the standard model is not sufficient. So that's the goal. The model with dark matter candidate and explain baryon asymmetry. That's what we want. Okay, before we will continue our trip towards this theory, let's look at the standard model from a little bit different point of view, namely from effective field theory point of view. So we assume the same symmetries as the standard model possessed, and the Lagrangian that is not limited to dimension 4 terms like in the standard model, but we include higher terms. Let's include dimension 6 up to dimension 6. There is one operator of dimension 5. For dimensional reasons, that must be 1 over lambda, just because O5. O5 is an operator made of standard model fields. However, dimension larger than 4, that means here 5. And also dimension 6, there are more operators of that sort. And now, the Higgs boson discovered, we know it's standard model-like, right? Its properties are very similar to what standard model predicts. So looking at this form, what would be the natural first intuition? What would that say? It would say that the lambda is probably large. Lambda is large, all those non-standard things, right? Those operators, lambda 5 and that, they are non-standard in that sense that they don't exist in the standard model. They will be suppressed and it's fine. And naively, it seems that this is the only possibility, and this is indeed explored by many of us, right? People are using effective field theory. This is exactly the scenario in which lambda is large, this is suppressed. effective field theory is applicable, but it's kind of boring, right? Everything is sent far away. Is there another possibility? Is it possible to have an extension that has such that there exists a Higgs boson that is standard model-like, and that the scale is not TeV or multi-TeV, but it's 500 GeV, 300 GeV? Is that possible? Let's ask this question. And after some experience, you would say, perhaps indeed, if the extension is rich enough, it could. And it turns out that indeed, it's possible. It's called alignment limit, and I will not define those things now. I'm just flashing here to advertise the ultimate goal, which is to advocate multi-doublet models. So there will be possibility. So it's not true that the fact that the standard model, that the Higgs is standard model-like, that the lambda, the scale of new physics, must be much larger than electroweak scale. Good, and now let's go through simple extensions. Of course, one can enlarge gauge symmetries. So there are grand unified theories. There are less ambitious possibilities, but very attractive, like left-right symmetric models. So the gauge models based on SU2 left cross SU2 right cross U1. That in the standard model, remember that parity is broken by hand, just by representations that we put. Here, parity is broken spontaneously. So it's nice. One can also even add U1 prime. I'm saying even because it's not particularly attractive possibility, but who knows? Maybe nature is such that the Z prime would exist. There are, of course, extra fermions, vector-like fermions or right-handed neutrinos, various possibilities. But eventually there is also possibility that there are extra Higgs bosons. And there exists an important constraint on extensions of the Higgs sector. Namely, remember there is a parameter, there is no battery, right, new battery, because this is almost gone. Right? Namely, rho parameter, mw square over mz square cosine square theta w. This parameter in the standard model at the tree level is 1. It's calculable and it's 1. At the loop level, there are corrections, but it's actually a nice example of finite corrections. They are finite corrections, but small because they are loop coupling suppressed. And now one can calculate this rho, assuming without imposing or requiring just doublets, but let's add general Higgs multiplets with T's weak isospin, so it could be either doublet, if it's doublet T is half, it could be triplet, etc., and third components. And if you require this to be 1, you will find the following solution. 1 is T equal 1/2, so this is just a doublet Higgs. And another one is, I don't remember, 8 or 9 higher dimensional representation, in which rho is naturally 1 at the tree level. So that naturally favors doublets, because in doublets you can check that easily. If you use just doublets, then rho stays 1 at the tree level. So therefore data rho experiment, I didn't say that, rho experimental is 1 roughly. So doublets are favored. Something else? or at least, yeah, are favored. What else? What else is allowed? I said 9 or 8, but that's not what I mean. There is a very trivial solution. Singlets, right? Someone said that, singlets. So something that has no SU2 quantum numbers. Then of course, T's are 0, it doesn't contribute. So extra singlets. So that is where I'm trying to brought you. The logic behind this is exactly illustrated in this slide. Rho is experimentally close to be 1. That favors doublets and singlets. Scalar, right? Spin 0. Note that if we indeed introduced new singlets and new doublets, then there would be some sort of similarity between spin 0 sector, scalar sector, and fermions, right? With fermions, everything is sitting in doublets and singlets. Left-handed doublets, right-handed singlets. And something similar may happen in here. Okay, so that brought us to those singlets, and I will go through details very soon. Namely, for instance, adding a real scalar field. If you impose, remember, dark matter must be stable. So stable with respect to decays. It cannot decay. So if there is an appropriate symmetry introduced, I will define it later, then indeed this real scalar, its excitations could be dark matter particles. Now another option is that this singlet scalar is complex field, and that is more interesting option because that allows to explain naturally the absence of the search for so-called direct detection experiments for dark matter. So scattering of dark matter against nuclei in underground laboratories. This is being searched for years, and result is negative. The limits on the cross-section are stronger and stronger. The cross-section must be smaller and smaller. So this model explains that nicely. And also, adding doublets, as you will see very soon, provides an option for extra CP sources. So it seems that those... Oh, excellent. Yeah, I know. I have the same. Oops. We are not in a hurry. Good. Thank you very much. Very, very good. I'm not sure it's very good, but good. So the fact is that introducing singlets and doublets allows to solve both dark matter issue and CP violation, and let's see how does it go in details. This is simple, so I encourage you to make an effort and follow, because it's really simple. So let's add real singlet scalar, and we denote it by S. The potential for this model would be the following. Phi is a standard model, so this is just a standard model potential. This is mass term and the quartic term for the scalar, and there is an interaction. It's called portal interaction between the scalar and the Higgs. And you see, if not, I omitted certain terms that are in principle possible, right? For instance, cubic. There is no S to the third power. This is not there because I want to have a model that has this Z2 symmetry. Z2 symmetry, and under Z2 S goes into minus S, and therefore S cube is absent, and therefore S is dark matter candidate. So that's, in spite of its simplicity, this model in certain regions of parameter is still allowed. But there is this other model that I mentioned, complex singlet. So let's add, again, the standard model, right? This is standard model. And we add the S, but now S is complex, and let's make it charged under certain global U1. So S goes into phase times S. This is global U1, right? Not gauge, global U1. There is, of course, mass term, cubic term, the portal, but I added here something a little bit unusual. This is not what we teach in our courses, usually, because this is, you see, there is no absolute value. It's not absolute value squared, it's S squared. So this term is not symmetric under S. Right? Everything that has absolute value is symmetric, obviously, because this phase just disappears. But this one is not. However, it's dimension 2 operator. This is so-called soft breaking. So it's a soft breaking of this U1, and the advantage of soft breaking is the following. If we have, usually where we have a theory, we must include all terms allowed by symmetry in order to make it renormalizable. However, if you break this symmetry softly, so I'm not introducing higher terms like S to the fourth, but only I stop at S squared, then the model remains renormalizable. These are, fundamental theories proven by Zimmermann and long time ago. So adding those terms, the renormalization does not require to introduce other terms that break. This is, one can limit that at this term. So the model is renormalizable. Now, if you parameterize S in that way, V sub S is the vacuum expectation value of S. It has a real part and the imaginary part, and then one can choose the phase of S that is such that Vs is real. Another thing is that I'm imposing charge conjugation symmetry, so S going to into S star must be a symmetry. Therefore, mu is really real, and this symmetry means, you see, that means that real part of S doesn't change sign, but imaginary part of S does change sign, right, under this transformation. Therefore, that implies stability of S. And another important thing, we are breaking global symmetry, spontaneously breaking global symmetry. Vs is non-zero. So this U1 is spontaneously broken. So usually we have Goldstone bosons, massless Goldstone bosons, and of course we don't want massless Goldstone bosons. But in this case, because this is not symmetric, it's a pseudo-Goldstone boson. It's not a Goldstone boson, it's a pseudo-Goldstone boson because of this term, because this term breaks explicitly but softly this symmetry. So this is the pseudo-Goldstone. Okay, so we have, and in this model there would be standard model Higgs, but there would be also another neutral Higgs that originates from this real part, phi sub S, and A is a candidate for dark matter. And now the important and peculiar thing. You derive Feynman rules for those fields, and then you find out that this A, actually A square, so two A fields, coupled to Higgses, there are, remember, two Higgses, H1 and H2, in such a way that there is a mixing angle. I don't want to go into details. There must be mixing angles because mass matrix is non-diagonal, so that is necessary. But you see, what is important here is that this coupling is proportional to mass of this Higgs squared. R is the mixing, it's orthogonal mixing matrix. And now you calculate the scattering, the direct detection search for dark matter. So scattering of A, dark matter, against nuclei. There are two diagrams at the tree level with exchange of H1 and H2. And using this vertex, you sum that. You sum them. Because of orthogonality, there will be sine from here, cosine from there. They combine to sine to alpha. Fn is some form factor that is not relevant here. And there are, because of orthogonality, there is a relative minus between those two diagrams. And see what happened. This M1 and 2 squared, M2 squared, they are coming from this vertex. So see what happened in the limit of small momentum transfer. If Q goes to 0, or if it's small, then those two terms cancel each other. And indeed, this is the case. We have calculated loop corrections because in this limit it's nice. Loop corrections are finite. And the leading term here, leading contribution are loop contributions indeed. So it's nice because that explains why our experimental colleagues are not finding the cross-section, non-zero cross-section, because there, I mean, hypothesis, of course, because there might be this model. Okay, so that was, so I showed you advantages of singlets, dark matter, and also this sophisticated version of dark matter, so complex. Complex is sophisticated because, I mean, it's not very sophisticated, but it's attractive because there is this cancellation. Then, okay. Nice thing is that if you introduced some other breaking, soft breaking by cubic terms, this cancellation is spoiled. So it's important to break it by quadratic terms. Okay, so now let's remember that there are doublets that are attractive, and doublets were founded, extra doublets were founded by T.D. Lee, who 50 years ago wrote this paper, Theory of Spontaneous T-violation. It's T-violation because all those theories that we considered are CP-T invariant, so something that is T-violating must be also CP-violating. For us, I would be calling that case CP-violating. So this is a model in which we extend scalar sector of the standard model by an extra doublet. The potential is becoming more complicated, right? You simply write everything what is allowed, all couplings. The allowed means gauge invariant, all gauge invariant couplings up to dimension 4. So there will be, for instance, mass term for the first one, for the second one, the mixed mass term, phi 1, phi 2. They are both doublets, so this is phi 1 dagger, phi 2 is a singlet, it's allowed. And then all possible quartic couplings, there are 7 of them. What is in red might be complex. Everything else are real, and these are complex, and it's important because of CP, of course. And then, so in this context, we have, first of all, we might have complex parameters in the potential, and the presence of a complex parameters implies CP violation. But there is also another option. It's a spontaneous CP violation, which is also possible. So real potential, but the vacuum expectation value, so the state minimum complex. So this conclusion here is that, okay, good, we have sources of CP violation. And remember that we want to have together dark matter and CP. So let's see what is possible. In this model with two doublets, there is the easiest parameterization of that is to make first a rotation by the angle beta that is defined here. V2 and V1 are vacuum expectation values of those two doublets, and if one does that, then one can separate Goldstone bosons that become longitudinal components of vector bosons and remaining. So remaining is a charge Higgs boson, and there is a combination of those chi's, and those chi's, remember, those chi's are complex fields, complex parts of the lower components. So in this model, we have three neutral scalars and a charge scalar. And there is a non-diagonal mass matrix. One has to diagonalize them and then construct a mass eigenstates. These are those capital H's. And the R is the mixing matrix, very similar to CKM matrix. In fact, I mean, this is simply orthogonal matrix. And now, something that perhaps is interesting. Namely, one should choose input parameters to describe this theory. And there are various options, of course. One could choose quartic couplings, for instance, and those mass parameters that were in the potential. But there is a better option, better in that sense that one could choose physical parameters. And this is what I'm doing here. I'm using masses, so 4 masses. E's are couplings of Higgses to vector bosons, and Q's are couplings of neutral Higgses to pairs of charged Higgs bosons. And it's important, this is something that you perhaps can memorize even, that there is a sum rule. Sum of squares of couplings of H1, H2, H3, everything squared, they sum to V squared, and V is 246. And now, we have a theory described by two doublets. Who is choosing what those doublets are? Can I use another doublet to describe the same theory? And the answer is yes, indeed. If you perform a rotation, U2 rotation between those two doublets, you choose another basis for this theory. But physics cannot change. It's like QED with changing phase of electron fields, something like that. And nothing can change. And here it's the same. And these are so-called basis, weak basis transformations. There is an analogy between this freedom of choosing a basis and the construction of so-called Yarlskog invariant. Yarlskog invariant comes from invariance with respect to rephasing fermionic fields, quark fields. This is very, very similar. There is one other thing that I must mention, namely, if you introduce extra doublets, you pay a price. there is fine with this rho parameter that stays 1. However, there is potential problem with Yukawas. These are standard model Yukawa couplings. If we remove this red alpha, then these are just standard model Yukawa couplings. Tilde means complex conjugation, contraction with epsilon, with antisymmetric tensor. However, if you have, and you remember the one of that, if you expand in the standard model this around the vacuum, then this contributes to up-type quark, right? Because no, this is, yeah, it does. And then this contributes to down-type quarks. It's easy, but if there are many doublets, then there would be many contributions of that sort. So the mass matrix for up would be a linear combination of matrices weighted by vacuum expectation values, and similarly for down. So if n is 2, so just 2 doublets, then this is the mass matrix for up, composed of those 2. This is for down, and the trouble is that we like to work in bases in which quark masses are diagonal, right? Well-defined masses. We don't like non-diagonal quark masses. Then, in the standard model, there is only one, either this or that. And of course, making mu diagonal makes gamma, these Yukawa couplings, diagonal as well. But if you have 2 of them contributing, 2 gammas are contributing to the mass, then you diagonalize mass, but it doesn't mean that you diagonalize both of those matrices contributing. So what appears are so-called flavor-changing neutral currents, and there are severely constrained. And there are ways to remove that, again, imposing appropriate Z2 symmetry. So this is the model that does that. And so now we can collect all those things. These are, again, couplings of Higgs bosons to vector bosons, parameterized by E's to Z's and to W's. And here I wrote those E's in terms of mixing angles explicitly. And we remember that they satisfy this sum rule. And now, important moment, Higgs alignment. I mentioned that, but now I want to explain. The Higgs alignment in this language means that it's a region in a parameter space such that there exists a Higgs boson that has exactly standard model couplings. And if it's possible to arrange things such, then we have found an example. Remember that slide on LHC interpretation. That is exactly the question that should be asked. Can we reproduce the same standard model couplings by this 2HDM? And the answer is yes, and you can easily see it. You can simply tell me what is this solution. You see, these are dimensionful. This has dimension of mass. In the standard model, E is just V. And so if we want to have one Higgs, let's say H1, that couples as the standard model does, then E1 must be 1. But look here. If E1 is 1, that simply means that E2 must be 0, E3 must be 0. But indeed, we do have standard model Higgs. So that is so-called alignment. And it turns out, now, what is alignment is an easy way of taking care of observational data. Data are telling that the Higgs is standard model-like. So doing theory, we go into alignment region and do algebra. That is much easier. But now, what would be the question natural to ask? Right? We have LHC, constraints from LHC. In other words, alignment is the preferred region of parameter space. But remember, we wanted to have CP violation. Right? So we should check now if there is a conflict between alignment, so the data, and CP. It might be the case. And this is doable in terms of using so-called weak basis invariants. So these are quantities that are physical and they parameterize CP. CP is those imaginary part of J1, J2, J3. They were found a long time ago by Lisbon colleagues, by Lavora and Silva. And the statement is that CP is conserved only if those numbers are zero. And this is something that is physical. This is not weak basis dependent. These are invariants. So we just insert e's to those invariants and calculate. It turns out that two of them are zero. The third one is in principle non-zero. And important consequence. The most popular model, version of the 2-Higgs-doublet model, is a model that has this Z2 symmetry that removes unwanted flavor-changing neutral currents. But this symmetry must be imposed on the whole Lagrangian, so not only Yukawas, but Yukawas and the potential. And it turns out that in this particular model, the requirement that there is a conflict between alignment, so the data, and the CP. In the limit, in this Z2 symmetric model, in the limit where Z2 is conserved, then there is no, this imaginary G30 is zero, so there is no CP violation. Therefore, that suggests, that pushes up towards theories that do not possess Z2. And therefore, they suggest that perhaps the solution of the flavor-changing neutral problem should be different than Z2. We can actually just tune couplings so that flavor-changing currents are eliminated. Now, the very final model is the following. You see, you add another doublet, phi 2, but this Z2, we assume the Z2 symmetry, so phi 2 goes into minus phi 2, unbroken, so the vacuum expectation value of phi 2 is 0. Then this model, those terms crossed are in conflict with the symmetry. They are not there. And in this model, the components of this second doublet, those two neutral guys, they are dark matter candidates. This doublet, it's called inner doublet, and this is an analog of this simple real scalar that I added before. So let's now conclude this HDM review. Violation of CP in the scalar potential is possible. Weak basis invariance of observables, it's something good to remember and it's very useful often. Flavor-changing neutral currents might appear, and the standard solution is this, but here, I'm jumping here, but the standard solution is not good because in this case the CP violation is in conflict with alignment, so with data, and there is this inert model that could be added and contains candidates dark matter, but not for CP violation. Okay, so we have gathered number of facts, properties of those models, and now we are ready to construct minimal models. So the very minimal model that contains what we want, that means CP violation and dark matter, is to add real or complex singlet plus 2HDM. That's the one possibility. The dark matter is coming from here. It's either this real scalar or it's an imaginary part of the complex singlet, while CP violation is coming from this 2HDM part. And the next to minimal is the model in which this singlet is replaced by the inner doublet. Inner doublet is the doublet that is odd under Z2 and odd under Z2, and this Z2 is unbroken, so that there are two fields that could be dark matter. And in this case, in this next to minimal, note what we got. We got 3 Higgs doublet model. 3, of course, is much better than 2, right? It's odd. So that brought us indeed to 3 Higgs doublet models, and perhaps it really makes sense to consider. You know, if you look at analogies between spin 0 and spin half, then for instance, you can think about Higgs doublets, each doublet that corresponds to each family. 3 families, 3 doublets. There are various possibilities to utilize those doublets and singlet as well in generalizing the scalar sector. And some of those things has been done, but within 3 Higgs doublets, things are more complicated. And for instance, there is no classification of symmetries of 3 Higgs doublets. So it is perhaps I still have time to tell you about this. So the singlet complex plus general 2HDM. This is something that should do everything. Singlet and be minimal. Singlet complex. It's complex because I want to have this global symmetry that will be softly broken, right? So I want to utilize this possibility. And the general 2HDM because I want to have CP violation. And it turns out that indeed this model possesses the same property of vanishing in the limit of 0 momentum transfer as in this simple model that I mentioned before. And it does have sources of CP violation that are denoted here by red, right? So these are complex numbers, and this is this U2 breaking mass. I'm sorry, U1 breaking mass. Okay. And so that was the minimal model. Then next to the minimal would be this 3 Higgs doublet model that we replace the singlet by the inner doublet, and I think I'm ready to conclude. So let's do it. Standard model is not perfect. The most severe problems to me are dark matter and the baryon asymmetry. There are other problems as well, like gravitational, like cosmological constant, or strong CP problem, or some other. But those two are definitely experimental issues. Standard model should be extended. Therefore, standard model should be extended. And extra scalar doublet, and if we decide to look for extensions of the spin zero sector, then singlets and doublets are favored. They are favored by this rho parameter that must be 1, or experimentally it's very close to 1. And for singlets and doublets, it is at 3 level, it is exactly 1. So therefore they are favored. Now, if we add singlets, then the property to remember is this. Complex scalar with soft breaking of a global symmetry. It was U1 in this example that I gave you. This is this breaking by S squared, not by absolute value of S, but by S squared. So this model has this attractive feature that the dark matter nucleus coupling is suppressed. This amplitude is vanishing because of this cancellation that I was mentioning. Another important thing is that the most popular Z2 symmetric HDM in the alignment limit, right, this is the alignment limit, doesn't have CP violation, and CP violation was our major motivation. So to cure this, we should abandon this Z2 and consider generic to HDM and stop thinking that the flavor changing neutral currents imply that the model is unacceptable. Okay, and then there are minimal pragmatic models of CP that contain CP violation and dark matter. It's real or complex singlet plus 2 HDM, and next to a minimal would be this real or complex replaced by the inert doublet. The inert doublet is this stable doublet and 2 HDM. In that way, we reached. That way, we reached 3 HDM models. That's all what I was going to tell you. Thank you very much.